Hello everyone, welcome back to lecture 4 in power circuit and electromechanics. So in this lecture, we'll be studying the electromechanical system. Okay, we'll be looking at magnetic circuit with just one moving member, and we will derive the mathematical model of lump parameter electromechanical system. Okay, we will have one or more set of electrical coils interacting to produce the force or the torque on the mechanical system. And in general, both current in the coils and the force or torque are time varying. A set of coupled electromechanical differential equation is obtained and put in state space form, convenient for computer simulation analysis and design. So let's have a look at the system in figure 4.1. So here we have N turn with the current I going, and we have a closed magnetic core with the cross-sectional area A here, and this is the average line, flux line, okay, the C contour with the length of L. Okay, so if you remember, this is the model when we cut through the structure. So the contour C here will have an area S taking S at the peripheral, and we have the wire here going out here on this side and going in on this side. So I showed you before in a live stream session that on the left hand side of this ampere circuit law, we will have height L, where L is the length of this contour C, and H is the magnetic field intensity, and N is number of turn, and I is the current inside that coil. When we apply the Faraday law, okay, we will have the left hand side is the induced voltage, the total induced voltage in this loop, and on the right hand side it will be d lambda by dt, with where lambda is the flux linkage. Okay, I will show you later the application of Gauss law. It depends on the specific geometry. Okay, and the force equation will lead to the KCL that you already know. So we mentioned Ohm 4 equation in the Maxwell equations system. Okay, now this is the structure of an electromechanical system, where on the left hand side you have the electrical system with lumped parameters. When we say lumped parameter, we don't have any distributed parameters. So the total inductance, for example, can be specified by just one value of L, and the total resistance of the circuit can be specified by just one R. Okay, so that's why we call it lump parameter. On the right hand side we have a mechanical system also with lump parameters. So on the electrical side we have variables voltage, current, and flux linkage. On the mechanical system we will have the force and the displacement, or the torque and the rotational angle. They come together. Okay, they come in pairs. So you either have F and X or T and theta. So between them is an electromechanical coupling environment, and in our case the coupling environment will be the magnetic field and the magnetic structure. So first let's have a look at the translational system. Okay, in translational system, our moving part can move in one direction. It's not rotating, it just move in a straight direction like this. Okay, left, right, or down, up, down. So we can say that the displacement is x. Okay, and we will need a force to create that displacement x, and therefore the flux linkage is a function of the current and the displacement, the mechanical displacement. When the geometry is simple, we can apply Faraday's law, and we will see that V equal d lambda by dt will now consist of two components. The first component is called transformer voltage, okay, because it doesn't have anything related to the speed or the displacement. The second component is called speed voltage, because it consists of dx by dt, which is speed. Okay. Now we define an electrically linear system where we can specify flux linkage as Lx multiplied by I. So here the self-inductance only depends on the displacement. Okay, it doesn't depend on the current. So for a given x, it's a linear function of current. That's why we say it's electrically linear. And therefore, when we calculate V by calculating d lambda by dt, we will have this expression with these components. So when the system has no moving part, it means x is a constant. Okay, so L will be constant too, and lambda will be Li, and therefore we only have this first component. The second component doesn't exist because dx by dt is 0. Okay. Now if we generalize it for multiple port system, every port or every coil, we will have one induced voltage Vk calculated by d lambda k by dt, and we can express it's a function of n current and m variable, a mechanical variable. The force and the flux linkage can be the function of ohm variable as well. So this is the end of part 1.